So in this section at the very beginning, the first thing that I was showing you was if you add a common ion, a substance that's already present, if you add that to a system that's in equilibrium, ultimately what we found out is that it is going to affect the pH of that particular system. And so we said here, if we added cyanide to this particular reaction, we found out using Le Chatelier's principle that the pH of that solution would end up going up. And so let's take a look at that mathematically. Let's actually figure out how much of an effect that common ion would have on a solution, that on the pH. So what we're going to do is take this first example. We're going to calculate the pH of just a regular HF solution. So this is not a common ion situation. This is just a standard 1 molar HF solution. Calculate the pH just like we learned how to do in chapter 16. And then once we get that pH calculated, we're going to calculate the pH of a solution that is also 1 molar HF but has this sodium fluoride common ion present. With the presence of the common ion in this second solution, the pH should be different. It should change. So we're going to be able to compare how much it's changed. So let's start with the first problem, calculating the pH of the 1 molar HF solution. Again, this is what we learned how to do in chapter 16, so this is a review. We're going to start by, we have to use an ice table, so we have to start by writing a balanced equation using the substance that we have, HF, and this is always plus H2O in equilibrium. We have to predict our products. We have a hint. The problem is giving us a Ka, which is our hint that this is an acid. And as you know, acids always produce H3O plus in solution. So that's one of our products. And the second product that we get in this reaction, we have to figure out ourselves what that second product is. So we're going to ask ourselves, how did that H3O plus get formed? Looking at the reactants, we can see that HF moved one of its hydrogens over to the H2O plus. And when it did that, the HF turned into F minus. So there's our balanced equation. We're ready to make an ice table for that equation. The initial amount of HF is 1 molar, and initially we have no products. Some of that HF is going to react, but we don't know how much, so we're going to call it X. And when we reach equilibrium, we're going to have 1.0 minus X HF, which we're going to assume that X is really, really small, and the concentration is just 1.0. And our H3O plus and F minus concentrations are X. In order to calculate the pH, we need to know what X is because that is our H3O plus concentration. So to solve for X, we're going to write an equilibrium expression, H3O plus times F minus over HF, and we're going to plug in what we know. Our Ka, 7.2 times 10 to the minus 4, X for both H3O plus and F minus, so that's X squared on top, over 1, our value of HF. And so now we're just going to solve for X. That is going to be 7.2 times 10 to the minus 4 times 1. And then take the square root. X is 0.0268. That is the H3O plus concentration. So pH is the negative log of the H3O plus concentration, X, 0.0268. Which is 1.57. So that's just our standard pH of our HF solution. Now moving on to the next part, we're going to calculate the pH of this same solution after we've added 0.5 molar NaF. NaF has an ion in common with HF. Their common ion is the F minus ion. Both HF and NAF have F minus in common. So to do this pH calculation, we're going to do the same thing. We're going to write a balanced equation, and we can just copy the one that we've already written, HF plus H2O in equilibrium with H3O plus and F minus. And we're going to make an ice table. And we're going to plug in our initial quantities. So our initial quantity of HF is 1. Our initial quantity of H3O plus is 0. And our initial quantity of F minus is 0.5. That's coming from this initial amount that we were given to start with. The change in this reaction is still going to be minus X plus X plus X. At equilibrium, it's still going to be 1 minus X. We assume X is very small, so it's 1. H3O plus is X. And fluoride F minus is 0.5 plus X. But again, we assume X is very small, so it's just 0.5. To calculate the pH of the solution, again, we just need to solve for X because pH is going to be the negative log of H3O plus, which is represented by X. So we're going to write an equilibrium expression. Ka is H3O plus times F minus over HF. We're going to plug in as much as we can. The Ka hasn't changed. Ka is still 7.2 times 10 to the minus 4. H3O plus, we don't know what it is, it's X. F minus is 0.5. And HF is 1. So we can simplify this a little bit. 7.2 times 10 to the minus 4 is 0.5x. We can solve for x. X is 0.0014. The pH is the negative log of 0.0014. Again, that's because the pH is the negative log of H3O plus, and we just calculated the concentration of H3O plus. And the pH of this solution is 2.84. So the pH has gone up from the original solution. When you have a common ion, like in this problem that we just did, and you're being asked to calculate the pH, you can use the ice table method like we just did. It's always going to work every single time. You can also use the Henderson-Hasselbalch equation. That would work for this as well. And so I didn't leave myself a lot of room to write the Henderson-Hasselbalch on here, but I want to show you using the Henderson-Hasselbalch as well. The Henderson-Hasselbalch equation is pH equals pKa plus the log of the concentration of the base, I'm just going to abbreviate B, over the acid A. The pKa is the negative log of the Ka, so it's the negative log of 7.2 times 10 to the minus 4, plus the log of the concentration of the base. What's our base? Let's go back up to our balanced equation. HF is our acid, and that means water is our base. H3O plus is our conjugate acid. F minus is our conjugate base. So we want to use, we're not going to use water as the base. We don't even know what the concentration of that is. It doesn't even have a concentration. So we're using the concentration of our conjugate base, 0.5, over the concentration of our acid, which is 1.0. So let's work the math out on that. 0.5 divided by 1 is 0.5. Take the log of that, For that part, I got negative 0.3. And then over here, let's calculate the pKa, the negative log of 7.2 times 10 to the minus 4. That is 3.14. Let's see what we get. This comes out to 2.84. Perfect. So again, you can use either an ice table and this method that you already know from chapter 16, or you can use Henderson-Hasselbalch, which is clearly a lot faster, but sometimes it's more comfortable to just use the methods that you already know.